So this will be your example 2 based on gas cycles. Okay, based on gas cycles. So this is constant pressure cycle or the closed gas turbine unit. Closed gas turbine unit. So the first thing is let us take a look at the example, and let us go to the questions. Okay. So I don't know why the pen is not functioning. Okay, in a gas turbine unit, that means a closed gas turbine unit, A is drawn at 1.02 bar and 15 degrees C, and it is compressed to 6.12 bar. Then calculate the thermal efficiency and the work ratio of the ideal constant pressure cycle when the maximum cycle temperature is limited to 800 degrees C. So basically, when I solve questions on gas cycles, usually I put it in table form. Okay, so it is easier for you to manage. Okay, and then your work later on will not be so messy and complicated. Okay, so that is why I teach you using tabular method. That means put all the data into a table. Okay, let's say for example, 0.1, what pressure, what volume, temperature, and then 0.2, 0.3, and 0.4 like that. If let's say you go into the dual combustion cycle where you have 5 state points, because altogether there are 5 processes for dual combustion, then you will have a very lengthy work, which will make your work looks very messy. So based on my experience, usually I put it into a table form. Okay, so before that, what we need to know is the TS and PV. Every time when you start solving a problem on gas cycles, remember to draw your TS and PV diagram. So first is your TS. So on the TS, remember for constant pressure cycle, that means a closed gas turbine unit, there is always 2 isentropic. So you can see there are 2 vertical lines here. And then there are 2 curves here. These 2 curves represents the constant pressure process. So since there are 2 constant pressure process, so that is why I draw 2 curves here and 2 vertical lines here. Okay, and remember also in the direction of increasing entropy is where you have your heat supply, and in the direction of decreasing entropy is where you have your heat rejected. So 2 to 3, okay, in these diagrams I didn't put in the arrows, so you can see by 1, 2, 3, 4 go in this order, so you know that the arrow or the flow path is from state point 2 to 3, so it's in the direction of increasing entropy. So 2 to 3 should be your heat supply, 4 to 1 should be your heat rejected, because from 4 to 1 the arrow, okay, will be in the direction of decreasing entropy. Remember, increased entropy is heat supply, decrease in entropy is heat rejected. So when you refer to state point 1, 2, and 3, 4, these lines are vertical. That means the entropy S3 equals to S4, and the entropy S1 equals to S2. So therefore, there will be no heat flow from 1, 2, and 3, 4. So in the case, if you want to know the thermal efficiency or the network out, so definitely you will have to find out the heat supply and the heat rejected. So to find out the heat supply and the heat rejected, the only 2 places that you can refer, the only 2 processes that you can refer is 2 to 3 and 4 to 1, not 1, 2, and 3, 4. Okay, so basically that is what you need. That is why you need a TS diagram. So on the PV diagram, remember, again, I repeat, 2 constant pressure and 2 isentropic. So you can see the curve for PV diagram for the entropy is, the slope is greater than usually when you draw a temperature curve on the PV diagram. So the entropy curve usually are greater in slope. That means it's steeper as compared to the temperature on a PV diagram. So PV diagram, you have pressure and volume already. So the only 2 things that you have to know is the entropy and the temperature line, how it looks like on the PV diagram, which I've shown you on the previous slides. Okay, so these 2 is your constant entropy line. or the constant entropy curve. Or you can say that 1, 2, and 3 to 4 here, you can put an arrow or an indicator that they are following the law of PV to the power of gamma. Power gamma equals to C, where gamma is equals to adiabatic index. So 2 to 3 here is constant pressure, 4 to 1 is constant pressure, 1 to 2 is isentropic compression, 3 to 4 is isentropic expansion. So in order to know compression and expansion process, it is better for you to refer to the PV diagram where you can see, okay, the decreasing volume from 1 to 2 and the increasing volume from 3 to 4. If you have drawn in the arrows, you will be able to see or to view it much more clearer. Okay. So this is the table which I mentioned just now. Okay, so usually I will put a table like that with pressure, volume, and temperature. And then, so since we have 4 points, so what I do is usually I put in 1, 2, 3, 4 state points. And then what I need to do is I fill up whatever that is given in the question into the table first. Now you see, okay, let us look back to the question. In a gas turbine unit, A is drawn this temperature. So that means your point 1 pressure is this, your point 1 temperature is this. Okay, so you put in your pressure 1.02 bar and your temperature 288. Okay, and your temperature 288. And then we know that the pressure of point 1 and point 4 are the same. So that is why I put 1.02 and 1.02 here first for point 1 and point 4. Okay, then after that, you have the temperature 288, which you take 273 plus 15. 273 plus 15, converting it to Kelvin. So you put it as 288 here. And then the last one is the maximum cycle temperature. So based on your TS diagram, so now you can see 1, 2, 3, 4. Based at looking at the diagram, you can see the highest point is 0.3. So that means the highest temperature is at 0.3, so which is 800. 800 plus 273, it will give you a temperature of 1073 in Kelvin. So the things that is labeled in red or written in red, those are the unknowns. And then I have put in the numbers 1, 2, 3, 4, 5, 6. So you can you don't have to go into you don't have to follow my orders. Okay, you can go here as first and here as second, up to you. But why I put this first or as the first one is because when you look at this row here itself, there is only one unknown here. Because you know 102 and 288, the only one unknown is 0.8104. Okay, so it's easier for me to refer to this state point 1 itself. Okay, so by using ideal gas law, either is PV equals to RT or PV equals to MRT. You can use PV equals to MRT when the question does not give you any mass or does not ask you to find any mass. So if the question have given you a mass or they ask you to find a mass, then your volume should be in meter cube. Otherwise, if let's say they didn't give you any mass or they didn't ask you to find any mass, so that means that is why I put volume here as a specific volume in meter cube per kg. So at this state point 1 here, there are only 2 unknowns. So, and since no mass or they are not asking you to find mass, so we can straight away use ideal gas law of PV equals to RT, not PV equals to MRT. Okay. So first thing is we have to find out this volume. So you can find out the volume by using PV equals to RT for based on state point 1 itself. So V1 is your subject. So A is standard, R for A is standard 0.287. Your temperature is 288. Okay, so your pressure, okay, is 1.02 bar. Okay, 1.02 bar. Why is multiplied by 100 here? Is because you are converting the bar to kilo. Because on top here, 0.287 is kilo. So if you want to change bar to kilo, usually you times it with 10 to the power of 2. That means 100. So you get a volume of 0.8104. So once you have got your volume, remember immediately write it, fill it up here. Okay, write it into the table and put it at the space 1 here. Okay, for the volume. Then part 2. Now remember, okay, you can also go to straight go to point 3, out the next volume as well. Okay, to find out the next volume as well straight away. Okay, that is your step 2 maybe. Okay, my step 2 is different. So which I have indicated here. It depends because it's very flexible. Okay, it depends on how you solve, but then you have to refer to the table to see there are how many unknowns that is inside the table, and then see what you have to apply in order to find the rest of the data. Okay, so what I did was, okay, I refers to 1 to 2, which is the isentropic. So remember isentropic, there are 3 forms which we can use. Okay, the pressure volume relationship, which is shown here, the pressure temperature relationship, and the temperature volume relationship. Okay, so you can use those for isentropic to find out whatever which is unknown on the next point. So if let's say, for example, you are using formulas like this, that means you are looking at a process. When you are using formula like this, that means you are referring to one state point. So when you are referring to a process, then you have to include both the points. So why I take this, because 1 to 2 here is isentropic. So I can use this formula, and it's isentropic, and we have already known, and in addition, we have already known these 2 pressure. And I have already known these 2 and this volume. But at state point 2, these 2 are unknowns. So I can use these 2 pressure with this volume to find out the unknown volume here by referring to this isentropic property relationship formula, PVT relationship. Okay, so changing the V2, now V2 is our unknown. So changing the V2 as to be the subject, So manipulating the equation, solving the problem by putting in your gamma for A is standard 1.4. So you got the next volume, that is V2. So once you have got this 0.2254, okay, straight away fill it up here. Then you've got the pressure, you've got the volume with an unknown temperature. So when you refer to this state point 2 itself, so you have got already 2. So to find the third value, I can refer to straight away the ideal gas law for state point 2. Or if you want to continue with the isentropic, means the pressure and the temperature, you can do so. You can also find out the same temperature. Or you can straight away, by applying these 2 values here, straight away use the ideal gas law to find out the temperature of T2. That is this. So your subject is T2, and when you put in your pressure 6.12, that is in bar, so that is why times 10 power 2, then multiply by the volume which you have found, okay, and then divided by the R 871 or 0.287. You don't have to times 10 power 3, even though it's kilo, because you have converted 6.12 bar here to kilo also as well. So what you get will be temperature 480.64 Kelvin here. Okay, then after that, now you look at your point 3. Your point 3 have this and this. So straight away you can go to part 4 here to find out this volume. Okay, applying ideal gas law also. So you will be able to find out, okay, why they go to T4 first, yeah. Oh, on this order is wrong. Oh my, let me see. Okay, so you follow this order, part 4. This is part 4. This is part 6. Part 4, sorry, the order is wrong. Okay, I put the order wrongly. So part 4, you use this formula to find out this volume here. So once you have done that, found this, straight away write it down here. So 1, 2, 3, full information. You got already full information. So now you want to find values of this and this at 0.4. So that means this 2 is unknown. These 2 values here are unknowns. So when these 2 values are unknowns, So you refers to isentropic process again, 3 to 4. Okay, 3 to 4, isentropic. So 3 to 4 here. Okay, so that is why I use, this is part 5, part 4, part 5, yeah. So this relationship air pressure and volume to find out the volume. Remember, when we use this, it has to be isentropic. Okay, it has to be the vertical line in the TS diagram. Okay, the isentropic. And gamma for A should be 1.4. So once you have found the V4 here, then you can again apply this ideal gas law to find out the T4. Okay, so once these are all filled up, then you go for what the question wants you to find. Okay, so since now you have got everything on the table, first thing is your heat supply. Now remember, heat supply is in the direction of increasing volume. Okay, 2 to 3 is increasing volume. 1, 2 no heat flow. 3, 4 also no heat flow. There's no heat flow from state point 1 to 2 and state point 3 to 4. So the only heat flow is 2 to 3 and 4 to 1. Where 2 to 3 you have heat supply. Okay, so and it's constant pressure. Remember how we got this formula just now, yeah? Cp T3 minus T2. Remember for A, specific capacity at constant pressure. Remember how we formed this formula just now in the theory part, the explanation part of the constant pressure cycle. Okay, Cp for A is 1.005 is standard. So put in the temperature and T3 and T2 which you have found, T3 and T2. Then you got your heat supply. Okay, then the next thing is to find out heat rejected. Why I find heat supply and heat rejected? Because I need to find out the network out, then to find out the thermal efficiency. Okay, so it is step-by-step work. Cp again, now this time 4 to 1. 4 to 1 you refer to TS. Remember TS is heat flow, PV is work done. So 4 to 1, this is constant pressure again. So decreasing entropy. Decreasing entropy means it's heat rejected. So you Cp, constant pressure, T4 minus T1. So you have got your T4 and your T1 as well. So therefore from there you get your heat rejected. So then you can find a network out by taking heat supply minus heat rejected. So that is 238.52. Then after that, you can find a thermal efficiency by taking network out over heat supply. Yeah. Okay, so that is the thermal efficiency. So that is the constant pressure work. Okay, constant pressure work. So that means 2 to 3. If you, let's say you want to find the area or the work from 2 to 3, that is based on internal reversible. So the area of the PV diagram is actually equals to work. So you take the height multiplied by the base. The base is V3 minus V2. So the height is P2 from the origin to this is your height. So if you want to find the area under 2 to 3, it should be a rectangle. So the height multiplied by the base 2 to 3. So you will get your work based on this 2 to 3 if you are considering internal reversible. And then adiabatic expansion for work done, adiabatic expansion for the work 3 to 4, okay, 3 to 4. Okay, you actually can use CP33 minus T4 as well. You can use CPT3 minus T4, or you can use this formula here that is based on integration method, which you find area under the curve from 3 to 4. Okay, integration method to find area under the curve in your PV diagram from 3 to 4, because area of PV is work. So you need the expansion and the expansion, and I will tell you why. What is the reason why we find out the expansion work 2, 3, and 3, 4. Now 4, 1, and 1, 2, they are compression work. 4, 1, and 1, 2 is compression. Okay, only 2 to 3 and 3 to 4 is expansion work, because you look at the volume. 2 to 3, you can see the volume increase from V2 to V3. Okay, your graph, the analysis of graph must be good enough by now, yeah, because you're an engineering students. So 2 to 3 shows an increasing volume, 3 to 4 increasing volume. Increasing means expansion. So we find both expansion work. I'll tell you why we need to find out expansion work. Because we need to find work ratio. Work ratio is defined as net work over gross work expansion. Gross work expansion means total expansion work. So your expansion work based on the PV is only 2 to 3 and 3 to 4, where 2 to 3 is a constant pressure work, okay, and 3 to 4 is your isentropic work. Okay, you can find this formula by using integration method to find out area under the curve for 3 to 4, where 3 to 4 follows the law of PV to the power of gamma equals to C. So from there, you will be able to find out both the work. So if you don't want to, let's say, using integration method to prove, okay, so you can straight away apply this formula to find out the work, or you can apply CP T3 minus T4. So you can find both the expansion work. So you add up both the expansion work to give you the gross work expansion. Okay, so work ratio, remember, work ratio is defined as net work out over gross work expansion. That is why we need to find out the gross work expansion. So the net work out is found here, 238.52. Okay, so divided by your gross work expansion, so you get the work ratio 0.521. Okay, thank you. If you have any questions, you can ask me, or you can put on the comment section of the YouTube contents, my YouTube content. Thank you. Bye-bye.